Welcome to Strength of Materials N6. Today's video is on deflection of beams. This is something that you already began to learn about in Strength of Materials N5, and so you will find that some of the things I am going to talk about are very familiar to you. However, I am not going to assume that everybody knows and understands the stuff very well, that everybody remembers very well what they did in Strength N5. I am still going to lay down the foundations just so that everybody can be up to speed and we can all look at deflection of beams from a Strength of Materials N6 perspective together and with the same level of ease and with the same level of understanding. And so let's begin. First, I am going to talk about the different types of loadings that you can have on a beam and how those will affect the loads on the beam, okay? And particularly the moment of resistance, okay? But before we get there, I need to remind you of the bending equation. And that is an equation that is written like that, but you can also write it like this, okay? So this is one and the same equation, but it is written in different ways, okay? Arranged in different ways, but it's the same equation, okay? And so in this equation, M is the bending moment or the moment of resistance. I is the area moment of inertia. Sigma is the bending stress. Y is the distance from the neutral axis, okay? And what we mean by the distance from the neutral axis is that in some questions they may ask you to find the stresses at a certain location in the beam, okay? And so if that is the case, then you will need to find the distance from the neutral axis to that location, and that is what we refer to as Y, the distance from the neutral axis. R is the radius of curvature, E is the Young's modulus, and Z that you see here is the section modulus, and it's given by this equation here. Z is equal to the moment of resistance divided by the bending stress, and it's also equal to the area moment of inertia divided by the distance from the neutral axis. So either this or that will give you the section modulus Z, okay? Very, very important. Now, let us look at loadings, but before we do, I will remind you that when you deal with a problem on beams, it's going to be a cantilever beam or it will be a simply supported beam, okay? So when we deal with cantilevers, the first type of loading that you can have on a cantilever beam is one where you have a point load acting at the end of the beam, the free end of the beam, to be more specific. So if we have a beam here that's got a length L, L is the length of the beam, and we have a point load that's got a magnitude of W acting at the free end of the beam, then the moment of resistance, M, is going to be equal to W. W is the magnitude of the point load multiplied by the length of the beam. The second case is when you have a distributed load, a UDL, acting over the full length of the cantilever. And in that case, the moment of resistance, M, is going to be equal to the magnitude of the UDL, which is small w, multiplied by the square of the length of the beam, and all of that divided by 2, okay? And finally, you have a case where you have a combination of these two cases. If you look here, this is a cantilever beam that's got a length L, and it is acted upon by a point load at its free end, which is the case that we have here, combined with a distributed load over its full length, which is the case that we have there. So if you look carefully, you will see that the loading that we have on the beam here is a combination of these two loadings, okay? And because it is a combination of these two loadings, if we want to find the moment of resistance for a situation like that, it's just going to be a combination of the moments of resistance that you have in the previous two cases, here and there. So the moment of resistance for all this is just the sum of the two moments of resistance for the previous two cases. Okay, so that M will be equal to WL, which is what we have here, plus small WL squared over 2, which is what we have here. Okay, and that's all really that I need to show you as far as cantilevers are concerned. The next type of loadings is on simply supported beams. And the first case we're going to look at is when you have a simply supported beam with a point load acting at the middle of the beam. First, to distinguish between a cantilever beam and a simply supported beam, a cantilever beam is a beam that is planted maybe in a wall, okay? It is completely fixed on one end and free on the other. A simply supported beam is a beam that is resting on two supports, okay? It is just freely resting on two supports. The supports can be rollers or they can be maybe the end of a wall, but the beam is just resting freely on those two supports. Usually the supports are at the ends of the beam, okay? Far left and far right. And that is why you see here in this picture, I am drawing these two reactions. These just justify the fact that you have supports at the ends of the beam, okay? And the length of the beam is L, and the first case, as I said, is when you have a point load acting at the middle of the beam. And when that is the case, the moment of resistance is given by the magnitude of that point load multiplied by the length of the beam divided by 4. The next case we're going to look at is when you have a UDL acting over the full length of the beam. And in this case, if we want to find the magnitude of the moment of resistance, that is going to be given by the magnitude of the UDL, which is given by small w, multiplied by the square of the length of the beam, and all of that divided by 8. The next case we're looking at is a combination of the previous two cases, okay? And as you can see, you have a point load acting at the middle of the beam, but combined with a UDL that is acting over the full length of the beam. And in this case, as it was the case earlier, all you need to do is to combine the moment of resistance of the previous two cases, okay? So that will give you WL over 4 plus small WL squared over 8, okay? It's just this moment of resistance plus that moment of resistance, because as you can see, this is a combination of these two cases, okay? And lastly, what we have is a situation where you have a point load, excuse me, acting not in the middle of the beam, but at some distance from the left end and at some distance from the right end of the beam. So A is the distance between the place where the load is acting and the left end of the beam, and B is the distance between the place where the point load is acting and the right end of the beam. And as you can see here, these distances are not equal, and because that is the case, how do we then find the moment of resistance? The equation is actually quite simple. The moment of resistance is going to be equal to the magnitude of that point load multiplied by A multiplied by B and divided by the length of the beam. Now, this equation is particularly important because it helps you find the moment of resistance regardless of where the point load is being applied. And of course, this is really interesting and very useful in practical applications, okay? And so, let us now look at centroids and moments of inertia. Very important. Now, this is something that you did in Strength of Materials N5, but I am just going to revisit that to make sure that you understand this before I carry on with the rest of what I have for you today. The reason is because in most of the problems on deflection of beams, what you will first need to do is to find the moment of inertia. And you cannot find the moment of inertia without locating the centroid. So it's important to remember how we find the location of the centroid and also how we then find the moment of inertia. So let's say you have this section, okay? It's got the shape of a T, okay? and that's why some people may refer to it as a T-section. And the top part is generally referred to as the flange, this top part here. And the part at the bottom here is referred to as the web. Okay, it's very, very important. Now, if you have to find the centroid of something like that, of this whole section, the easiest way to do that is to divide the section into shapes for which the centroid is easy to find. If you look carefully at that section, you will see that you can easily divide it into two rectangles, okay? The flange will be your first rectangle and the web will be your second rectangle, okay? And so, if you do that, then you can locate the centroid of each of those shapes and then use an equation that I will show you shortly to locate the centroid of the whole section. So we will call the flange, the area of the flange, we will call that A1, okay? The area of the web, we will call that A2, all right? So as you can see, the flange is a rectangle, the web is also a rectangle. So the location of the centroids is very easy to find. It's right in the middle of the rectangle. When you have a rectangle, the centroid is in the middle of the rectangle. So the neutral axis passes through the centroid, always. Any shape that you have, the neutral axis will pass through the centroid. And at this point, it's important for me to remind you that you always have two neutral axes. One is horizontal and the other one is vertical. But both of them will always pass through the neutral axis. So for instance, here the horizontal neutral axis for the top rectangle, which is the flange, will pass through the centroid of that top rectangle. Okay, it's very important to remember. The neutral axis always passes through the centroid, and you always have two of them, the horizontal neutral axis and the vertical neutral axis. In some of the questions, you may need to use both, and in other questions, you will just have to use one of them, okay, to be able to solve whatever it is that they ask you to find. Okay, so now what's important for me to say here is that the centroid of the flange here, the top rectangle that you see, this is not the centroid of the full section. Okay, this is just the centroid of the top shape, the top rectangle. And then we also have the centroid of the bottom rectangle here, and its horizontal neutral axis will also pass through that. Okay, now if we have to find the centroid of this particular section, it's important to remember that when you're dealing with a section that has got an axis of symmetry, a section that's got an axis of symmetry will have its centroid on the axis of symmetry. Okay, it's really important to understand that. A section that has got two axes of symmetry will have the centroid at the intersection of the two axes of symmetry. So what is it that we refer to as an axis of symmetry? An axis of symmetry is that line that you can draw through the section in such a way that on either side of the line, the shape that you see is a mirror image of the shape on the other side of the line. Okay, so it's like that. On either side of the line, you have shapes that are mirror images of each other. Okay, so for instance, if you look at this T section that we have here, if you draw a vertical line through the middle of the section like that, you can see that the shape on the right is a mirror image of the shape on the left. So this vertical line that you will draw here is an axis of symmetry. However, if you look at this T section, you will see that it does not have a horizontal axis of symmetry, because there is no way you could draw a line in such a way that what you will have at the top of the line will be a mirror image of what you have at the bottom of the line. Okay, so the centroid is always on the axis of symmetry. If you happen to have two of them, like for instance a square will have two axes of symmetry. Therefore, the centroid will be at the intersection of the two axes of symmetry, and that is of course the center of the square. Okay, so in this case we only have one axis of symmetry, which is vertical. So we already know that the centroid is somewhere along this line, okay? But the only thing that we need to find is where exactly on this line is the centroid. And for that, we will need to find the y coordinate of the centroid.